we would like to find the Taylor series for ln x in powers of x minus 1. First thing we should think then when we see this question is let's write out what this Taylor series will look like. And because it's powers of x minus 1, we're thinking of the Taylor series which involves powers of x minus a. And that Taylor series looks like this. So f of x is f of a plus f dash of a gives x minus a plus f dash dash of a over 2 factorial brackets x minus a squared. We'll do one more term plus f dash 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 of a over 3 factorial x minus a cubed dot dot dot. So that's our Taylor series. We'll just go to the 4th term. What this tells us is these things we need to know. The successive derivatives of f at that point A. It doesn't take us to do too much thinking to think, well, if we want powers of x minus 1 and we need x minus a in our Taylor series, that means a has to be 1. And it kind of goes without saying in this question as well that f of x has to be ln x. So ln x is our f of x here. Well, let's do some thinking now then. If we put ln x in here and start differentiating, we'll see what needs to happen. So f of x is ln x. We want to differentiate it 3 times. So first time, f dash of x, ln x will go to 1 over x. The second time we differentiate f dash dash of x, we should get minus 1 over x squared. And the third time we differentiate f triple dash of x. Well, if you imagine this is minus x to the power of minus 2, the minus 2 will come out, so we'll get 2 over x cubed, 2x to the minus 3. Great. At the moment we've got these derivatives of f of x. We would like to be a bit more specific though. We would like f and its derivatives at the point A, which we know here as 1. So next we have to work out those derivatives and plug in 1. So let's write that here. F at 1 is just ln 1, and ln 1 is 0. F dash at 1, dash at 1 is 1 over 1, which is just 1. F dash dash at 1 is minus 1 over 1 squared. So that gives us minus 1, and f triple dash at 1 is 2 over 1 cubed, which gives us 2. Great, well these are the coefficients that are going to go into our Taylor series, and we just need to be mindful we don't forget the factorials. It's a really easy mistake to make forgetting those. When we write this out then, our Taylor series, we should have, so f of x, or our ln x, is going to be f of a, well that's 0 first of all, plus f dash at 1 is just 1, so that's the 1 that's going to go here. Got 1 brackets x minus 1. Well, our next coefficient is minus 1, so it's going to be minus 1 for the second derivative over 2 factorial. 2 factorial is just 2. So minus 1 half x minus 1 squared, and if we can squeeze our cubed term in there, the third derivative is 2, so it's going to be 2 over 3 factorial, 2 over 3 factorial x minus 1 cubed. And I've put dot 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 after because of course this continues on to infinity if we want. I should be a bit better. Instead of writing f of x, ln x should go here. So our ln x, if we just sort this out a bit nicer, well, we can get rid of the 0. So we've just got x minus 1 as our first term. Our second term, we're happy it's x minus 1 squared over 2. And it should be a minus as well. So minus x minus 1 squared and then just thinking about the coefficient for our cubed term, 3 factorial is 6 because it's 3 times 2 times 1. So 2 over 3 factorial just simplifies to 1/3. So you should have plus x minus 1 cubed over 3 dot dot dot. Part B of this question is really, really nice. We would like to prove that the limit as x approaches 1 of ln x over x minus 1 is 1. Okay, if we think about this first of all though, why are we not allowed to do this just by reasoning about it? And it's because ln x, as x goes to 1, this goes to 0. And as x goes to 1, x minus 1 also goes to 0. So we've got this kind of indeterminate form here, where we're not actually sure what's going on. We're not allowed to just say 0 over 0 equals 1, because we're not quite sure about their behaviour around this limit. Let's do it with a Taylor series though, and see how this works. So can we rewrite this limit in terms of a Taylor series? Let's try it. So the limit as x goes to 1 of ln x over x minus 1 well, we just worked out the Taylor series for ln x. So let's write that out as a new and improved limit. So x goes to 1. And for ln x, remember we had 0 plus x minus 1 over 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. Let's do one more term because we know what the next term is going to look like. X, well, this should be a minus x minus 1 power 4 over 4 dot dot dot. And this should all be in this nice big brackets. And on the bottom will be x minus 1. Okay, well this is where Taylor series is really, really helpful for limits. Because if we consider here, as x goes to 1, all of these brackets are all going to go to 0 because x minus 1 is going to approach 0. And if we look for a nice cancellation, we can see something on both the top and the bottom. Any term with an x minus 1 will cancel with this x minus 1 on the bottom. So all these powers are going to reduce by 1. The 2 will go to 1, the 3 will go to 2, the 4 will go to 3, and so on. Let's write below then what we've actually changed this Taylor series to get. So we've got the limit as x goes to 1. The 0, we could forget about that to begin with. It doesn't actually do anything for us. The x minus 1 over x minus 1 has just gone to a 1. We can forget about our denominator. That doesn't really matter to us either anymore because it's just 1 now. We cancelled out one lot of this brackets. But what's really important to us here is we've got plus x minus 1 over 2. minus x minus 1 over 2. And then we've got plus x minus 1 squared over 3 minus x minus 1 cubed over 4, and so on. All that's changed about our limit is we took out this factor of x minus 1, so each of the brackets, their power has decreased by 1. This is where this key idea comes back to us though. Anytime you see an x minus 1, because we're going to the limit where x tends towards 1, these brackets will go to 0. And we should write something down to reason about that, just to make our thinking really clear. Something like this would be really nice. Any power of x minus 1 will have to go to 0. So any term in x minus 1 will go to 0. I'm going to put an exclamation mark because that's so important for us. Any term in x minus 1 will have to tend to 0. What this means for us then is the limit is just this 1 that's left over. So at this point, when we've concluded that any term in x minus 1 will tend to 0, well, now we're happy to say this thing's the only thing left over, so our limit must be 1. And we're finished on that question.